Uh-huh.
Is there a way to have it so your packages are always installed?
They should be always installed.
Because I always have to keep installing Gmodel.
So when you load, when you say library
Yeah,
and library name, it says there is no such thing? Really?
yeah.
That's weird. That I don't have a good answer for, okay? So if the package is not installed, then it probably, it was either erased from the computer by, we're using system, Senu is using system, I believe it's called deep freeze, basically kind of preserves configuration of computers. So I don't know what really could be the reason. And are you using Bloomberg or a regular computer? Regular? Yeah, go figure. All right, so everybody downloaded the script from the previous class, right? Okay, so today we're going to continue. Reminder, here's what we did. Here's what the script is all about. We're looking at the, still we're doing classification tree, okay? And we're looking at the example with the bank. The bank wants to find out who are the target group of customers, bank customers, who are likely to accept the offer coming from the bank, unsolicited offer of a loan. So in other words, you receive a letter or the postcard in your mail that says, hey, we have low interest rates, go get a loan from us, right? So let's kind of run this code line by line, okay? A reminder what we did. And you still should have the file bank.csv in your folder data on the disk C, okay? So I'm assuming nobody cleaned their folders. So I'm going to run the first line, basically reading the code, the data in, okay? And then structure, well, I'm just going to run it, but not look into that. So then the next thing that we did is we calculated the counts, right? How many observations were in the bank file, do you remember? 5,000 records, right? And then we showed the count, so we said that out of 5,000 records, the majority, 4520, they didn't even react to the proposal, right, from the bank. And only 480 people somehow applied for the loan or contacted bank, something, right, something happened, okay? And in proportions, next line, prop table, that means that 9.6%, close to 10% of customers did something with this offer, and the majority, over 90%, they just basically threw it in the garbage, right? And then we loaded the G models, right? G models we're using primarily for cross-table function, right? So that we can take two categorical variables and create a cross-tab of these two variables. And we looked at is the variable education affecting customers' propensity to agree to the loan, right? And what we found, I believe, is that among bachelors, yes, customers, right, only 4.4% respond to the offer. But among doctors and MS customers, 13.7 and 13 close, right? So it's about 3 times higher, right, than compared to the BS, right? So therefore, experience, or education, could be an important variable, right? And then the next line that we ran was right here. We said, is online banking, if people are doing online banking, is that important? Does that affect in any way? Are they likely to apply or not? And we found that among both groups, right, they're similar. 9.4% among people who don't do online banking, and 9.8 among people who do online banking, right? So it's very similar, so therefore probably whether or not you're doing online banking is not that influential, important, right? And after that, here's the creative part, right, sort of. We decided that from now on, the way how we're going to build our classification trees is take the data set and split it into unequal parts, right? Part number one, bigger, we call training set. Why? Because we're using that to build our model or to train our model, right? And then after that, the whole reason why we have validation set is so that we can say, hey, this is the data that was never shown to the model. Let's see how it does on the data it never saw before, okay? And if we see big differences in the performance, then we're going to say, ooh, look at that. Typically what happens is on your training set, the accuracy is higher than on the validation set, okay? If it's close enough, then we're going to say, yeah, that's fine, okay? Accuracy is comparable, so therefore our model probably performs just as good on previously unseen data as it does on the one that we used for the training purposes. But if there is a big gap between accuracy, then we're going to say, ooh, the model performs much better on the training set, which means that it approximates training set much closer than it does the validation set that it never saw before, right? Which means that the model probably suffers from overfitting, right? It follows closely training set, but not so closely things that it never saw before. That was the whole idea, okay? And next thing, just so that we have the same validation and training set, we did this line, right? Set seed 100. It generates a random number, which is used to create a sample, right? A random sample. Out of 5,000 records in the set, I create sample of 4,000 numbers, right? So 80% essentially, right? So I'm going to use random sample to extract the training set, and I run this line. It's supposed to give me 4,000 numbers between 0 to 5,000, right? And after that, this is the part where we create the training and validation set. We're saying all the records from my original data set, bank data, that have indices, number of records, right? The record index number. Indices given by this random sample, that's going to be my validation training set, 4,000 records, right? So if I run this line, it's supposed to give me training set, and whatever is left, that's why we use the minus sign right here, is becoming validation set, right? It's going to be 1,000 records. And the next line that we did was this one. We said, take the training set. Note that here I'm not using bank data anymore, right? I'm using training set to train the data, okay? And my target is personal loan. That's the name of the column in my data set that says yes, no. Did they take the loan or did they not take the loan? And this is a classification model, hence class, right? So, but before that, I think I need to load a couple of libraries. So I built a model, and after that, I can show the model, and that was the model, right? And here we said that actually, what the bank might be interested in, yes or no. Bank might be interested in customers who said yes, right? People who actually responded to the offer of the loan, right? Because if it's a no, what does it mean? That means that we send a card or a letter, and they threw it in the garbage, right? That's it. This is where the story ends. There is no loan application. There is no income for the bank. Nothing really, okay? So we're primarily focused on these people, okay? So this is our model. And let's go ahead and, so everybody up to speed right now, right? That's kind of a reminder what we did last week. Don? Object personal loan not found. Did you load the data? You did? Hold on. Coming right up. Download the data set from Scholar, okay? This one is new. It has all the right stuff. Okay? Alright, and we're back. Okay, so I built the model, right? And I used for that which data set? Training data set, okay? Let's see how accurately my model performs on my training data set, okay? So I'm going to actually calculate two things, and then I'm going to show you two more things how we can measure model performance. Okay, but first things first, right? So right now I'm going to create. What do I need in order to calculate accuracy and related measure, which is called how, by the way? Accuracy, and another one is misclassification rate. What do I need? Confusion matrix, that's right. And to build confusion matrix, what do I need? Predictions, right? I need to use my model to predict the outcomes, right? I know the outcomes, right? They are inside my training set, column personal loan. Now I have to use my model to predict these outcomes and compare what's predicted versus what actually happened, okay? So, but first thing, I'm going to predict outcomes on training set, right? The same set that I used to train my model, okay? Which function do we use to predict the yes-no? Function predict, right? I told you that always we build a model, but we always use the function predict, right? So how should I call this beautiful variable? Let's call it training set predictions, because that's what it is, right? Training underscore set underscore predictions, okay? And I'm using the function, raise it a little bit. Okay, I'm using the function predict. So to use the function predict, I need to send it three things, right? Thing number one is the model itself, right? What do I call my model? It's called bank underscore classification tree model, right? That's the name. Then I'm telling the function which data set to use. It's going to be the same training set, right? So, but I have to say new data, okay? Even if it's old data, I still have to say new data. New data equals, what did I call it, training set? I believe so, right? Training set. And the last thing is my model is really classification tree, right? Not a regression tree. We're going to discuss regression trees hopefully on Monday. Okay? That's probably going to be the last lecture that's using this algorithm. CART, it's called, right? Classification and regression trees. So far we did CART, right? Oh no, CAT. So far we did CAT. Classification, not even CAT, CT classification tree, right? Excuse me. Alright, so training set, and now I have to say type of the prediction equals class, right? Class, meaning that the result should be yes, no, and not a number. Okay? Alright, go ahead and run this line. Control Enter, right? Or just simply click the run button. And there you go. You should not see any red color, right? If it's all blue, that means that things worked out beautifully, okay? Now, I believe I loaded the library G model for the confusion matrix, right? Because it's going to be across the table, okay? So, now, let me go ahead and build, and I'm going to say exactly explicitly, right? Confusion matrix for training set, right? It's all about training set so far, right? Training set, okay? All right, so I have the predictions, I have hopefully the real thing. So let's see what happens, okay? Cross tab, and I'm crossing two categorical variables, right? Yes, no predictions, which I just created. Training set predictions. Training set predictions versus the real yes, no classifications, right? How do I access them? Which data do I use? Training set, right? Training set. And inside the training set, I'm picking the personal loan, right? It's all about this column, personal loan, okay? My predictions are about that. Training set, personal loan. Bam, okay? And here is my confusion matrix. Now, here's what's going to happen, okay? Probably I'm going to hate myself for using time for this, but hey, it's all education, right? So how about that? Instead of training set, I'm going to use the entire bank data. Don't do that because it's stupid, okay? You'll see in a minute. Bank underscore data. And it's going to give me an error. It's going to say X and Y, your variables X and Y must be the same length. Why are they not the same length? Because training, how many predictions I have in my training set predictions? 4,000, right? It's the same as the training set. How many personal loan yes, no's I have in my bank data? 5,000, right? That's basically the reason why it tells me that it's not going to work. So I have to use my training set, okay? Bam. All right. So let's calculate accuracy and misclassification rate, okay? So, well, tell me, how many true positives do I have? 342. How many true negatives? 3607 out of 4,000, right? That's it. That's your accuracy, okay? So let me go ahead and let's see. Can I get? Oh God, where is that? One note. This one right here. Okay. Probably still has the stuff from our So therefore, accuracy is going to be. Oh God, I forgot what the numbers were. Can you tell me? .342, 3607 out of 4,000, right? So whatever that is. But there is an alternative way how I can find it, right? So let me go back. So let's see. Here is how I can interpret my results, right? In each cell there are 5 numbers, and here's how to interpret them. So n out of table total is essentially the count divided by table total, which is 4,000, right? So what I can do really is I can take this number, which is percentage of true negatives, right? And this number, which is percentage of true positives, and just add them together, okay? That's kind of alternative way how you can quickly calculate the accuracy. So true negatives 90.2%, true positives is 8.6. So if I add them together, it looks like I'm going to get 98.8, right? And if you calculate that using calculator, that ratio should be 0.988 or 98.8%. Is that high accuracy? It's huge, right? Accuracy is unbelievably high. My model is PDG. Pretty darn good, right? So, can you guess, or rather calculate, what my misclassification rate is going to be? 0.012, right? Because misclassification plus accuracy should add up to 1.0. Okay, so well, I can calculate that actually. So my true false positives is 26. False negatives 25, right? So really, I have 26 plus 25 divided by the same 4,000, right? Or it's going to be 41 out of 4,000. And yeah, I'm pretty sure if you do the math, then you will end up with 0.012. So 1.2% of my observations, my model is misclassifying, okay? Classifies incorrectly. We did that before, right? So that's nothing new. Okay, let me tell you about 2 more measures of accuracy, okay? They're called sensitivity and specificity. So let's start with sensitivity. Okay? And another one is specificity. Okay, sensitivity first. Let me ask you this, ladies and gentlemen. Are answers yes and no equally valuable for the bank? What's bank more interested in? Customers who said yes or customers who said no? Customers who said yes, because that means loans, that means interest income, right? Customers who said no, they send them the materials, they throw it in the garbage, done. That's where the story ends, right? Of customers, one of the categories, specifically category yes, is much more valuable for the bank to know, as opposed to who said no, right? No means this is it. No, dead end, right? But if it's yes, then yeah, it's income, right, for the bank. So therefore, the categories are not equivalent. Yes is much better for the bank than no, okay? This is where the primary focus of attention is, on the customers who said yes. And specificity is what percentage of our preferred response, which is yes, was predicted by the model correctly. So, hear me out. True or false? Altogether, among 4,000 customers, I had 367 yeses. True or no? This is what actually happened. Yes, no, right? So 367 yeses and 3,633 yeses, right? Oh, no. Right? So that in total, that's 4,000. So in my sample of 4,000 customers, 367 were yeses, right? Out of them, 342 were predicted correctly as a yes, and in 25 cases, my model messed up, right? It was a yes, but it was predicted as a no, correct? So in other words, out of these people who I want to predict all of them correctly, right? In actuality, correctly were predicted 342, right? And that, my friends, is sensitivity, okay? What percentage of actual responses, true responses of interest, were predicted by the model correctly, okay? So in my case, the responses of interest are in column 1, in column 2, yeses, right? So, out of 367, 342 were predicted correctly. So, and that becomes my sensitivity, okay? 342 divided by, is it 367? 367, okay. And whatever percentage that is, I don't know, but I can easily find out if I go back to my matrix, right? I'm talking about total in columns, right? It's all done in columns, right? So yeses, 367, that's my column total, and that would be n divided by column total, and that would be fourth number from the top or second from the bottom, right? So in other words, this one right here, okay? So sensitivity of my model, how sensitive it is to the category, to the responses that are primarily my interest, okay? Primarily the focus of my attention, that is given by that number. So 932, right? So my sensitivity is 0.932 or 93.2%. Now question, do I want my sensitivity to be high or low? What do you think? High, right? Because it's percentage of responses of interest which are correctly predicted by the model. I want it to be high, right? I want to predict as many yeses out of all yeses that are out there, okay? So sensitivity should be high. Accuracy should be high. Misclassification rate should be low. Okay, specificity. Now we need to remember that there is a second one, right? There is a second category which is not our primary kind of target, not that much of interest for us. That's no responses, right? Still, I want my model to be able to predict those no responses nicely, okay? And that's called sensitivity. Specificity, okay? So specificity is this. Out of 3,633 people who said no in the sample, I correctly predicted 3607, right? And I messed up in 26 cases, right? So my specificity is actually this number, also second from the bottom, but now for my true negative responses, okay? Because it's also out of column total. So in total I had 3633 no responses, and my model picked up correctly 3607, okay? Which represents 99.3%, which is again pretty darn good, okay? So I'm going to write it out. 3607. So specificity is 3607 divided by, 3633 was that total for the column? Yep. And that would 0.993 if I remember correctly, right? 0.993 or 99.3%. And again, just like sensitivity, I want my specificity to be high, okay? So, therefore, here is the stuff, okay? Here are the 4 measures of accuracy, or model performance, I should say, okay? One of them is accuracy, which takes into consideration both yes and no responses, right? This classification I want to be as low as possible, because these are errors, essentially, that I'm making, right? Sensitivity high means that the category which you are focusing on primarily is being predicted nicely, right? If it's high, that means that you're doing a good job, your model, okay? Specificity is not focused, primary focus, people who said no, but I still want it to be high, okay? So, what do we see? Our model has actually really good performance, right? Too good to be true, almost, okay? What can be that an indication of? Overfitting could be, right? Yeah, overtraining. Overtraining actually is a good term. Yeah, overfitting. So could it be that my model actually follows my training data way too close? And therefore, if you give it some data that it's never seen before, it will mess up. And it will start accumulating bigger errors just because it's a different noise, right? So am I fitting the noise along with the signals too much, okay? Who knows? Let's find out, okay? So, any questions, by the way, about specificity and sensitivity? All right, well, let's go back, and let's create yet another confusion matrix, right? I want to calculate now accuracy, sensitivity, specificity, and misclassification rate for this model, how it performs on my validation set, right? That's why I set it aside. Okay, sometimes it's also called hold-out sample, because I'm making it and kind of holding out. Model doesn't see it. The only time when I use this data is when the model is ready. And now I'm saying, hey, look at this data. You've never seen it before. Let's see how you will perform. Okay. So, in order to create the confusion matrix, right? What do I need? Cross table, right? And for that I need predictions, right? I need to take my model and predict the outcomes, but on what data set? On validation set, right? So let me go ahead and put a comment here. Predictions on validation set. Okay? And I'm using the same function predict. Nothing is new in this world, right? So how did I call it? Training set predictions. I'm going to call it the same, but now validation set predictions. Okay? And as we already did today, I need to use the function predict. And function predict needs to receive 3 things from me, right? Thing number 1, the model. What do I call my model? Bank, classification, tree, model, right? It's the same model. Bank underscore classification tree model. What do I say for new data? Validation set, right? Use validation set as your new data. And what type of prediction to make? Class, right? Simple as that. Okay? So I'm going to run it. It should give me no red color. Means that it takes the validation data, and for each one of these 1,000 records, right, it creates yes or no prediction. But we also know what it was in actuality, right? It's hidden inside validation set, $, personal underscore loan column, right? That's the column that has the actual answers, yes or no. And now I'm going to create confusion matrix on validation set. And that would be cross table, right? Just like what we did before. Cross table. Of what and what? Validation predictions versus? Excellent. Validation set personal loan, right? So validation set predictions versus my validation set $ personal loan. What it was in actuality, right? The real thing. Okay, let's run it. Validation set predictions versus validation set personal loan. Everybody got it? Why not? You remember we dealt with X and Y are not the same before? And what was the reason? They should be 1,000 records each, right? So prediction, maybe you use training, so check your validation set predictions. You should use validation set as the data, not the training set. Okay? And then after that, you should take your validation set predictions and cross it with validation set personal loan. You do? Okay, let's look at that after class, because that shouldn't be happening, right? So here's how my model performs on the validation set. Okay, well, ladies and gentlemen, without writing down expressions, okay, without writing down numbers, tell me what is the accuracy of this confusion matrix? %, that's right. Everybody sees that? Why 98%? Because I have to add percentage of true negatives and percentage of true positives, right? So it's 87.7 plus 10.3, which is 98%, right? Accuracy is 98%. So what is misclassification rate? 2, right? And you can see it from here as well. Rate of false positives is 1%, and rate of false negatives is also 1%, right? So you can calculate it like this as well. 2% misclassification, 98% accuracy, okay? Let's go back to what it was before. Accuracy on the training set was 98.8, and now on my validation set, right, I'm going to put a big number, big letter V, right? 98%, and here it was 1.2, and now on the validation set it's 2%. Is there a big difference? Not really, right? So my model actually is not overfitting, right? If I would see accuracy dropping to, like, let's say 75, 80, right? And error, misclassification error going up to like 20, 25, 30%, and I'll say, whoa, look at that. So much worse. I'm overfitting, right? Not actually. It's pretty close, right? Okay, so last thing, let's take a look at sensitivity and specificity, right? Tell me, ladies and gents, how much is sensitivity of my model? No, where do I look? I look at the column totals, right, because this is where the actual yeses are, right? So out of 113, which were yeses in my validation set, 103 were predicted correctly, right? So n out of column totals is right here. So my model sensitivity is 91.2%. And model specificity is 98.9%, right? So let's compare it. So my sensitivity for the validation set is 91.2. And what was the specificity? 90. What was that? I don't remember. 98? No, it was some. Hold on. It was 98.9. Yeah, 98.9. Okay, 98.9%. Is there a big drop in my sensitivity and specificity? Not really, right? Within like 2 percentage points, which is fine. Okay. So this model turns out to be not too good to be true, but actually pretty good model, okay? Now, let me tell you the warning, okay? In actuality, this is too good of an example. You will never see that high accuracy, sensitivity, and specificity in the real world examples, okay? So the best probably that you can hope for is 75, 80, 85% accuracy. And sometimes the model does actually a better job predicting no's as opposed to yeses. And that would basically also throws off basically the performance. Okay, the model accuracy can be decent, but it's predicting no better than it predicts yes, not what you're looking for, right? Predicts the other category, other response better than it predicts what your primarily focus of attention is. Okay, not unusual, and we'll see examples like that later during the semester. Okay, I sense the disturbance in the force, which means we're out of time. Okay.